Let's start with one of the questions that we address in the DoubleZero economics module, which is how do link contributors actually get rewarded? So let's set up a simple little world to try and illustrate the core concepts. Let's say there are three cities, cities A, B, and C, and they all want to send traffic to their clockwise neighbor, A to B, B to C, and C back to A. And let's say for the sake of argument, they all want to send 1 gigabit of traffic, again, to their clockwise neighbor. Let's say in turn that the DoubleZero network contributors provide 4 links along this pathway. They provide 2 links between A and B, 1 link between B and C, and 1 link between A and C. And finally, let's say for the sake of argument that this top link between A and B is more performant than this bottom link between A and B. How might we actually incentivize network contributors and reward them in this model? Well, one way to reward them is on the basis of carried traffic. We'd say, okay, the top link and these other 2 parts of the triangle, they each carried 1 gigabit of traffic. Therefore, they should each get exactly 1/3 of the rewards. But is that all? Is that all we can do? In fact, this seems to have a lot of imperfections. For instance, there's clearly some value to redundancy. Despite that, this second, less performant link between A and B gets no rewards at all, so would never be incentivized in this naive model. Moreover, what if these links aren't actually delivering a lot of value above and beyond the public internet? Let's say B and C actually have excellent public internet connectivity between them, and the link that's provided by the network contributor, the private link, isn't that much better. Should that one party really get 1/3 of the total rewards? As we start to go through this exercise, you realize that this simple carried traffic model starts to break down pretty fast. And almost certainly 1/3, 1/3, 1/3 is the incorrect division. Well, instead, what the DoubleZero network does is we use a concept from cooperative game theory called Shapley values. Shapley values were invented by someone named Lloyd Shapley, who later actually won the Nobel Prize for it. And it's a nice way of actually parceling up value according to the marginal or the incremental contribution of each of these different network contributors. So to be very, very concrete, let's say there's now some public internet latency between these cities that we can measure. The only thing that we will pay network contributors for, and we will pay them roughly in proportion to how much more they beat the public internet latency. But that's not the only factor. The second factor, of course, is their ability to actually facilitate that amount of traffic that wants to transit between 2 cities. So in short, really what the value function is, what network contributors are getting paid for is their ability to increase bandwidth and reduce latency. If they can do that, if they can have large, wide superhighways that do substantially better than the public option, they get paid. And if they cannot, then they do not. Finally, when you sort of have this value function in this methodology, you end up even incentivizing a little bit of redundancy. Maybe not at outrageously generous levels, but if this bottom link in this example still has decent performance, still does somewhat better than the public internet, still has decent bandwidth, well, there is a counterfactual world where it's very, very valuable, and so there is a world where it gets paid, and that is in fact this world. And so that's how we think about the network contributions model, or the rewards for that, which is if they increase bandwidth and reduce latency over the public internet, they get paid. All right, if you enjoyed this content, just go to this website, economics.doublezero.xyz/overview to learn and comment more. All of the proposals there are public, and we'd be happy to hear from you.